basically, ZKBoo simulates the three-party MPC, in the ZKBoo, one plumer simulates three-party MPC, and it first.
You should use a phone as well.
Okay.
No.
Yes, and it decomposes the vector of the. So first, you want to send so when providing some input for a specific circuit, its output is the claimed public value. So you can see the input x is the witness value, and the output y is the public output. And C is restricted. C is tied to the proved LP statement. And
so these like the 1, 2, 3 things are the transcripts of the three different parties, basically. Is that the right sense?
Yeah. So it simulates three-party computation, and it means it's a share of the first party. So it decomposes the same vector of the input value into three shares.
Secret shares, like secret shares, or
yeah, it's additive secret shares.
Okay,
so as long as you have as long as you have only two of these three shares, you cannot recover the original input.
Oh, so it's 3 of 3. You need
yes.
Got it. Okay.
So
also, for context, for Giannis and Nico, this is ZKBoo, which is MPC in the head, which is basically a protocol roughly where you're like simulating. You should correct me if I'm wrong. Like simulating MPC, and making proofs about it. Is that correct?
No, so using simulated MPC to prove, like as a ZK proof, because you show that you only could have done that MPC step if you knew like the correct witness.
I see.
Okay, so thank you for introduction. and it decomposes the private input vector into three shares, and its best idea is it first simulates the MPC among these three parties for each gate. So we can represent its computation of so this function means it updates so it computes the share of the output wire for the ICE gate, and it depends on the actual gate type. So it depends on whether the ICE gate is FTP gate or some constant gate or multiplication gate.
Okay.
And so it denotes so for each gate and for each index of the party, it computes the output, the share of the output wire of the ICE gate, and so this J means the index of the output gate or its wire, and this is the vector of the share of the wire values for the ICE party, and it takes some required share of the input wires like this one, and algorithms it's some random types, so it's a seed randomness. And
so what is this I and I plus 1 business?
So
like it's like M belongs to set.
okay. So in this MPC, it assumes it's the ICE I think its ICE party's output share can be computed only from the ICE party's other share and the I plus 1's party's other share. So the first party's share is computed from the first party and the second party, and the second party's share is computed from the second and third party, and the third party's one is computed from third and first party.
Cool.
So it only needs to know the my own my holding wire share and the next party's share. And after it computes the share of the output wire for all party, so it wants to compute the it compose the output shares which returns the output share, and by adding them it can generate the output value. So this is a function to be evaluated, and we can update this protocol to the interactive ZK protocol, and later we can make it non-interactive using fiat Shamia transform. So you
I
can
see. Wait, so this like phi, is that phi? I'm really bad at Greek letters. The function.
Sorry.
What's the Greek letter function name? Phi.
Sorry.
Yeah.
So this means how to compute the share of the output fire for the ice skate. And
so this is basically a function that you derive. So if there's like some. Yeah. Wait, can we have like a simple? Is the next thing like a simple example? Yeah. Maybe
okay. So its definition is this way. So if the get is at some constant value, its definition it is computed like this way. So for example, it collects because if we only add constant to the first party's share, and when we aggregate all shares for this gate,
it'll all
its
work out.
its output should be equal to the input value plus this alpha. And you can see
interesting. So
yeah.
only in this case, only the first party's shares get constants added to them, basically.
Yes. And in the case of multiplying constant value, each party only need to constant this word. And addition is also simple because it only need to add its own shares for two input values.
Yeah.
And only for multiplication gate, it need to share it need to use the two parties shares like this one, and it is defined like this definition, and this L means the random generator function. So it generates a randomness unique to the I and the index I and the wire value C. So actually, you can think this is the output of some hash function.
Wait, how does this work? Wait, what is this? Yeah, I'm confused at how Ri, like how if it's a uniformly random function.
Yeah.
How does this multiplication like work?
So you can imagine this randomness is cancelled when adding all parties shares.
Oh, nice.
So for example, if this is
I
I,
right, so
yeah,
that's it. I see.
yeah,
Okay.
one it will be one C minus L.
Right.
Yeah.
So,
Yeah.
so then they like all subtract out.
Yeah.
Nice.
And when I equals 3 I plus 1 is equal to 1. Yeah. So
it's like R1 and then minus R2.
Yeah.
R2 minus R3. R3 minus R1. So
yes, exactly. Yes.
Nice.
And the other values are also added or cancelled, and its value should be equal to the multiplication of the original value of the wire A and the original value of the wire B. So this multiplication works.
Wait, how do the other ones cancel out?
But can you imagine like A plus B plus C, like A1 B1 C1 times A2 B2 C A2 plus B2 plus C2, then you get all the cross terms, which are all accounted for here,
Yeah.
as well as all of the like same terms, like the square terms, which are like accounted for in the in like whatever W1A times WIA times WIB.
WIA times.
Right, so like what you're gonna end with like two cross terms for each cross term and one square for each square. So you're in the end you're gonna have exactly the product you're looking for.
Fascinating. Nice. This is so good. Cool.
Yeah.
Yeah, this reminds me a lot of Vol. Like Vol is like also kind of like similar ideas to this, but they have a different like OLE tool that they use instead of like additive secret shares.
Yeah.
Nice. Okay, so so three parties do this. Okay,
Yes.
so this makes sense in the MPC setting, but
Yeah.
what's the head in the head?
Okay. So the point is
Sorry, also, do you guys have any questions? I'm
I'm-
zooming through this.
Okay. So in the ZKBoo protocol, the preview computes all of these three parties computation first in the commitment phase.
Yeah.
And in the actual ZKBoo protocol, it computes all of these wire values, share of the wire values for each party, and it makes the commitment of these wire values, and it sends this commitment and the output shares.
Oh, okay. Then it just like challenges the verifier. We do like Fiat Shamir challenges on the transcript.
Yeah. So the verifier requires open any two of the three views, and the prover then submits the randomness to open this commitment, and then verifier can also compute the output share wire shares of one party's view because in this computation one party's wire computation only requires its self shares, and the next party's shares.
Right. So you can't. It's still ZK because basically like it's not revealing anything because it's
Yes.
only 2/3.
Yes,
Okay.
because it's 3 of 3 empathy. So
Nice.
yeah, so
It's so good. Wow.
yeah, and it just checks whether the open value is the correct value of this computation, and by adding all of the output shares, it goes to the claimed output value, and finally its output of this wire value is go to this output share.
Wait, sorry, I'm still confused how this is a proof because, sorry, how is the challenge getting incorporated here?
So in the interactive setting, just the challenge is sampled by the verifier, but
Yeah.
in the actual non-interactive protocol, it is computed in your
Yeah,
fiat
some
Shamir.
Fiat Shamir.
So it computes the hash of these commitment values, and based on this value, it decides which index should be opened,
Which index means which gate or?
which party's view should be open. So
Okay.
it means which I should be open.
Sure.
And actually, if we only do this protocol only once, the program may be able to are able to make a fake proof by estimating the challenge value,
Right.
because it
Yeah.
only need to
Only three.
sample two output views. So the verifier, so we have to repeat this protocol to increase the probability of the
Ah, I
soundness.
see. Okay.
Here, so
Wait. So the prover does the whole commitment phase many times, or
Yeah.
is it just like the verifier?
The challenge many times, right?
here, I think it need to make a commitment many times.
Oh
Oh,
wow.
I see.
Yes, and so
So this whole protocol like only happens once on a transcript, basically.
yeah, so it only describes one challenging case, and we actually performs this protocol many times, and it says if we repeat this parameter so this copy of the ZKBoo protocol, we can get the soundness or
Yeah.
this soundness. So
So 256, or like what's the soundness goal? Like 100?
I think its value is actually, for example, 100 or 128.
Okay.
Yeah, because to achieve the 100 or 128 security level,
Yeah.
so it means we have to compute 128 times log to 3 minus 4 inverse values.
So how many is that in practice? Like
So we can compute.
math time.
Yeah.
Wait, nice. Okay, so
So I'm still confused about like, how do you use the commitments to prove that you did the protocol correctly? Like, so maybe I confused step 3 on verify or something.
wait, can I try to answer this?
Yeah.
Like, so the commitment you have at the end, so it's just like this A vector, like y1 and c1 and whatever that
Yeah.
stuff. You take a hash of that, and that determines like the index that you're challenging on, basically.
Yeah.
Which I guess encodes both like which party share you're gonna get and also
Yeah.
which gate you're opening up,
Sure. Oh, it also goes to gate.
right?
No, you open all gates.
Our gate is all of the gate is public, because scikit
Yeah.
is public.
Yeah, so you're opening.
Or, like,
So
which-
with a challenge, you're opening every gate for one party. Is that correct?
Yes. So
Or
it's
two
sure-
parties. Sorry.
So it actually opens one party's view, but to do that,
You need
it
two
requires
parties.
two need
Got it,
parties
okay, yeah,
or
fine.
variables. Yes.
So is it only at one gate or is it every single gate? Because this J index is that
It's I think
For every gate.
every gate.
So
Yes.
it's every
So it
single
says
gate, yeah.
it needs to check whether there's any gate which does not satisfy this which does not satisfy the correct relation of the input and output shares.
Oh wow. Okay, so the I see. Okay, I see why the verifier thing is linear now because
Yes.
you're doing all the gates and also
Yeah.
you're doing it like
Yeah.
100
Yeah,
times
yeah.
or whatever.
Yes.
So I still don't understand this. So they're trying to prove that the share of the jth gate that the ith person has is in fact correctly constructed from the two shares of the two people, and K. What is K?
K is
Or
random.
K is a random type, so it's a randomness to generate the. I think it's a each path is some random seed.
Wait, is that also generated Fiat Shamir wise? Because can't we like lie about this or something?
So sorry.
How are those random tapes generated?
I think it can the prover can compute these random types from actual randomness. So it's like a randomness when generating GK-SNAX proofs.
Wait, but what if the prover? What if I like lie about the randomness to like I don't know?
Yeah, like what if the randomness is like 0, 0, n or something?
So in that case, the prover cannot maintain the zero knowledge property, but I think it cannot make a fake proof, even if the random type is actually not random.
Oh, cool.
Because
so the randomness is just for ZK. It's like it's for your benefit.
I understand. Yeah, as far as I understand, it's only for ZK.
Cool.
ZK property.
Interesting. Nice.
Okay.
So now.
Yeah, so go back
Yes.
to the ZKBoo. Sorry,
Yeah.
so then given the two keys, but then I see. So sorry, but they only have the commitment, or they wait.
No, the verifier has like the random tapes as well, and also the whole W's, right?
Oh, because the verifier can have W and not reveal any of the information. But the verifier, if they have K, the verifier knows all the secret information, right?
The verifier knows the ith path is all randomness from the ith path is random type, but it cannot get the actual private input X because this is shared as additive 3 of 3 random shares, secret shellings.
Oh, I see. You only reveal 2 of the 3 keys.
Yes.
And you only reveal 2 of the 3 tapes.
Yes.
And so they can verify that the first person's tape matches what it should be from the 2 keys and 3 tapes. How do they verify?
No, 2 keys and 2 tapes.
Sorry, 2 keys and 2 tapes. How do they verify that the 2 keys that were revealed in fact correspond to the full additive key?
This is because it can compute the one part, all of the one part is wire value, share of the wire value from the self ith path is shared and the next path is shared this way. So even if it only reveals 2 paths even if it only reveals not 3 but 2 shares, it can compute the ith path shares completely, and it can check if this is corresponding to the first commitment value.
So I get that. So I get they send all the commitments and they only open 2 of the 3 commitments. But what I don't get is why can't I like it seems there's no verification done here that like K1 plus K2 plus K2 plus K3 is the original key. Like that's never being verified, right? Like what is stopping me from faking? Like I just commit to the wrong values of K or something like that, or like my K is just never added up to the main share.
So you mean it can force the unreviewed commitment and run them, right? So for example, if the verifier requests the first parties or first party and the second party shared, it can make any commitment for the third parties, and the verifier does not check.
Yeah, exactly.
This is correct. However, it cannot estimate which parties view should be opened before sending the commitment. So by repeating this process enough times, the probability that the malicious prover can estimate all of the requested view parties whose view is open is very small.
So maybe my question is, how hard is it once you've committed to something, like once you've committed to some set of W and K, how hard is it to generate a different set of W and K that are for the same commitment? I guess it's not possible.
Yes.
It's effectively not possible.
Yes,
Once you've committed, you have to open that commitment.
So I think this paper's answer is if we want to say the probability that the adversary can the adversary is lucky because it can estimate all of the requested index is about power of 128 so 100 minus 128 power of minus 128.
Yeah. So
Then we have to repeat these times.
So I get that we repeat it 128 times
Yeah.
or whatever that number is. I guess I'm not convinced that this proves knowledge of a satisfying witness yet in just a single. Let's say we do it once.
Well, it doesn't prove it once. Like it's just like there is like some probability, or like it's just like a repeated thing. It's like you can do it. You can like probably generate a fake one once. You can get lucky if they pick the right like third of your transcript that you did actually do correctly. But you can't generate all three of them correctly unless you do have a valid witness, right? Does that make sense? Like this log 2 base 3 minus 1, I'm sure we can derive really easily. It's just like you can fake one or two of them, but it's like very difficult to fake all three of them. Basically impossible. Okay, let's see. How do you derive this?
Okay, so maybe I have a different question. So in like protocol like Groth 16 or other protocols with commitments, you do some operation over the commitments to prove that something was done correctly, right? So you say, like, the pairing over the commitments holds or whatever it is. Here, we're not using the commitments in any way. We're just opening the commitments. So like, I would imagine that maybe there's something we're doing with like, we add 3 commitments of the keys and we homomorphically show that like all 3 commitments add to the main key or something like that. But here there's no operation being done over the commitments, just opening of 2 of the commitments. So I'm confused how we can prove all the statements, like all of the operations were done correctly. Like what if I just committed to fake values? I just committed to like, some K's that were incorrect and some W's that were incorrect, and okay, the gate relationship holds, so the gates were done correctly, but the keys are just like completely invalid or something.
Wait, like by keys you mean the K?
Yeah.
So those aren't keys, those are random numbers. Those are not keys. There's no keys in the setup. The W are the witness values. So for you to have like done this whole transcript and at the very end the outputs are correct, like it's a Boolean circuit, so the output's gonna be 1 if you satisfy it basically, right? Let's just stick in that world. Then at the very end, if like you recover the output from the final 3 values and it's 1, then the only way that all 3 transcripts were done correctly is if you actually have the valid witnesses for each of them. The keys are just like, this is just like random values that are being used for something. It is like, those are I think not important.
Okay, so maybe my better question is, I understand why this protocol proves step 3, but I don't understand why it proves step 2.
What do you mean step 2?
Like step 2 here is like what we did is we took our like input, like the actual input, and we divided it into 3 shares, like the x1, x2, x3 for each person. Now, what I don't understand is how is like the commitment opening proving that this was done correctly. Like, for instance, what I could have done.
You can just add up the first gate or something, right, and just prove that they were all. Oh wait, no, some of the inputs are private here. Wait, I think roughly the intuition here is like if you didn't do step 2 correctly, like you don't have correct inputs and like you didn't share them properly, like you're not going to be able to get to the end with a valid output, as well as like receiving challenges on many different indices of
because you would just fail some of the gates.
Yeah, you just like wouldn't get to the end with a 1 at the like Y.
I see. And
it doesn't need to prove that step because I guess he's also assuming the function phi is like written correctly for your circuit. Basically, it's like a soundness thing on the function. But
so if we think it concretely, or for example, so if we only have this as constant gate, and if the trigger maliciously generates each input shares, then I think the work of the Bayfire is like, if the Bayfire says please open the first practice and second practice pills, it will reveal the first and second input shares, and the Bayfire combines this one, and the Bayfire gets x1 plus alpha and x2 itself, and it computes and this x1 plus alpha will be the output the first party's output share, and the second one will be the same as the input share. Second party's input share. And the prover also need to submit all of the all parties' output shares in the commitment phase, and the verifier can check if the computed first party's output share is equal to the submitted one in the first one.
Yeah, so I got this. I got we verify all the gates on all the private shares.
Yeah.
I guess
did it not just answer your question by saying like you can't do the step 2 without having a valid one? Like it doesn't matter if you didn't do that correctly or not. Like it's just like you wouldn't be able to get to the end with an output of 1 and get challenged like 120.
Yeah. So maybe my question is it possible for like party 1 and party 2 to satisfy this gate relation, party 2 and party 3 to satisfy this gate relation, and party 1 and party 3 to satisfy this gate relation, and still you have somehow cheated the system?
No.
No.
Yeah.
Wait, because you can add everything together at every single step, and you'll just have the transcript. Like if you get rid of the additive secret shares, you'll just have the computation transcript. And if each of the pairs are doing it correctly, then you will it'll work.
Yeah. So I think as long as each gate satisfies the correctness property, when computing the so I think each input and output. So you can think it makes some constraints for each gate. So for example, this gate says even if input share is generated maliciously, its input and output shares should satisfy relation like.
Right.
Yeah.
I see. And if all the relations are satisfied, then I know that by adding all 3 of these people at the first step, I can construct the input that would satisfy the whole protocol. But I don't reveal enough shares to reveal this input.
Yes.
Well, this is a very pretty scheme. This is a very simple scheme.
It's so good.
Why was it not the first ZK scheme?
Wait, because the verifier, it's not a snark, it's a narc.
Yeah.
It's not succinct.
Wait, next question, Sora, is that like, okay, so if we put verification inside of a ZK circuit, aren't we fucked? Like,
because the verification is O of n.
The verification is just
and O of n times 128, or whatever that number is.
Yeah, isn't this gonna be like
a massive circuit?
Yeah.
Recursive circuit.
Yeah. So I think the recursive circuit requires each gate computation.
Yeah.
But if we set the native field, its actual computation is like for example,
it's just
native addition or multiplication or Poseidon, or for example Poseidon computation. So even
but it's still gonna be n constraints.
No, but he's saying the cost of computing this verification proof. Oh no, but
each of these gates, even if it's in the current field,
you're doing them in BM254 directly.
I know, but even then, it's still an addition in BM254 land. It's a multiplication in BM254 land. Also, wait, how does this work in finite fields? Wait, pause.
So
the multiplication gate, that seems pretty binary fixed, right?
But I don't think it's fixed to binary because it does not use any binary features.
There's nothing binary about this.
What about the multiplication?
That's fine. That isn't. Well, how's that binary?
Yeah.
Isn't that like it works? It clearly works with ones and zeros, but like it's less clear to me that
why? Just expand out the multiplication. Like, what about it doesn't work for bits?
I didn't really understand what you said, to be
honest.
Sorry,
so what this is proving, this binary multiplication gate is proving, is that like your 3 shares are like, I don't know, like A1, A2, A3, meaning input A split among the 3 people. Like, so what we should do is, if you add this value, like W1C plus W2C plus W3C, at the end should be the same as like the recombined A and the recombined B multiplying to give you C. Right? So that means like
so WIA plus WIB.
Yeah, exactly. So W1A plus W2A plus W3A all times, like that in parentheses, all times W2A plus W2b, sorry, W1b plus W2b plus W3b. Now let's expand out this multiplication, right? We get W1a.
What was that?
The TV, I think I touched it. It was
Oh, whoa.
It was W1a times W1b. That's like, okay, so let's multiply out the top all the terms like this, right?
Wait, pause. Let me just think about this. Okay, so
Maybe I'm more good to maths, but
wait, okay. So I think intuitively this makes sense, but then why do they say it's only binary?
Why do they say it's only binary? I don't know.
Is it just more efficient in binary or something?
But you understand that, right? Like if you multiply this three terms times 3 terms. Okay, sorry for touching you again. You get three terms like this, and then you get like 6 cross terms, right?
It's still beeping. Oh,
yeah, I think it's more clear.
nice.
Yeah, this is exactly
Yeah.
the thing I was saying. Yeah. Like this is the sum over all the shares of A, all the shares of B. You multiply it out. These are all the whatever. These are all the
I know
terms
what
I
you're
was saying
saying,
top
I
to
know what
bottom.
you're
These are all the cross terms, and this gives you the original thing we were talking about.
Wait. Okay, this all makes sense. I believe this math. Wait, but why is it binary?
Yeah. Why did they publish this paper for binary fields?
I
Who
don't
cares
I
about
don't
it?
know. This is why I asked Intel why this is called binary addition and multiplication.
And what did she say?
I have not guessed her answer.
Yingtao didn't respond, but Andrija was like, I don't know. Yeah, it seems like it should work for scalars
Yeah.
too. I think.
And did they implement it for only binary?
Did they only implement binary in their implementation on GitHub?
I'm not sure. I think we should check
Yeah.
information. Yes, but I think theoretically it is possible to extend this scheme for our arbitrary finite ring. Actually, the paper says.
Because it feels like the genius thing to do here is like to just do this in like 64-bit land, right? Or like 2 to the 64-bit finite field, and then additions become XORs. This is just like the Binius trick, which is that like hash functions are mostly XORs, additions in binary fields are XORs. So
your field is just 2 to the 64.
yeah, and you just do everything, all the XOR or whatever, 2 to the 16, whatever XOR thing that Hash-Shaw does. Why don't you just stay in that land? Is that answered in this paper? Or do they only do binary? I guess they only do binary circuits in this paper.
This paper only performs the binary things for our benchmark. So
Oh wait, they both use vectors.
They use vectors of 32 bits.
yes.
Okay, implementing the 2 algorithms. Wait, scroll down.
Bitwise XORs. Yeah. Okay. Oh.
And
Sorry. So it's not a field with 2 values. This is a field of size 2 to the 32.
No. They're just describing what SHA is. But it's unclear if they did that. So, no. It looks like they did all these guys. 192 ands. So
Yeah, but this is just the number of operations you're doing in the field size 2 to the 32.
No. I'm not sure if that's true.
Maybe yeah. It is.
They're just like that earlier description seems like it's just saying like this is what SHA is. It does it in 2 to the 32.
sorry. So this theoretically it says it works on arbitrary finite ring. So it means we don't have to assume this is a field. It can be just ring. So we can use, for example, our power of 30 or power 2 power of the 13 field. Ring.
That's a finite field too, right?
I think it's not finite field because it's not prime number, but
No,
it's a ring.
You can have finite fields with primes and primes to any power.
But I think it's an extension field.
Oh.
Yeah, but in this case, we don't have to use extension field for power of x, because it can be just a ring rather than finite field.
And the only difference between a ring and a field is that there's no inverse.
Because in the ring it does not have inverse for all values.
Right, that makes sense. Okay, cool, nice.
Yeah.
So we're chilling. Okay, nice. Wait, so did they just implement it 2 to the 32 land?
Yeah. So is the field size here 2 or 2 to the 32? In what they do?
I think its implementation uses 32 per 32
So it isn't 2 to the 32. So you're totally right.
So they already did this. Okay, so then.
Right.
Wait, they didn't explain how to do bitwise ands.
sorry. So
Oh no, they said it right here. Hence the two natural choices for the ring are 2 and 32. So it's the number of XORs dominates.
Ah, yeah.
Yeah.
So
I see.
yeah.
Oh, but since it. Oh.
I see. Add is free, but bitwise operators require a linear number of multiplication gates. I see.
That is
So
free,
XOR.
but bitwise operations require a linear number of multiplication gates.
That seems correct. Yeah, Benius gets around.
What does that
stuff.
even mean?
So I think free means it just addition, and addition does not need to use two parties or two parties or add shares, wire shares. So I think in this case XOR is just one addition and
Yeah.
it's very cheap. And in this other case it just so out of 32 bits integer is just one addition and it's so it
Wait,
says free because
It's free, but it's one gate.
yeah it's I think free means one addition gate.
I see.
Yeah.
Free means no additional gates.
Sorry, no one addition gate.
Yeah.
Oh.
So
Yeah.
so I see.
Yeah.
Wait, but isn't addition in a binary field XOR? Isn't that correct? Or sorry, binary ring, isn't it XOR?
Yes, because every addition is computed with mod 2. Yeah.
Or no, even in like 2 to the 32.
I don't think so because it's a bitwise XOR. So
Oh, bitwise.
Yeah.
No, like
but
yeah, adding is XORs, right?
so for example,
Mod 32. Mod 2 to 32.
so for example, if we have 0 1 and 0 1 plus the 1 should be 0 1 0 1 plus 0 1 should be 0 1 and 0 1 should be 0 0 is a case of bitwise XOR, but its addition is 1
Just
0 because it has
curious.
carry here.
I'm confused. One sec. I believe this, but wait. The whole thing about Benius is that XORs are easy. Okay, and also the reason that Benius doesn't need this linear number of gates is they do some like really clever shit with like towers of binary fields where they recursively do these operations into like 2 to the 32. They break it into two fields of 2 to the 16, and they do some like really clever combinations. So Benius is like it's in its own. It's doing its
So
own
is
thing.
Benius? Yeah, but Benius is some other like they don't like this is still potentially more elegant than Benius, is it?
Hard to define what elegant means here. This is clean as fuck, but Benius is also clean as fuck in its own ways. Field addition corresponds to the logical exclusive OR operation over these fields. Wait, I'm so confused. Anyway, let's just keep going through this. Okay, yeah. The thing I don't understand is that if you try to make a verifier for this, I see. So basically, the verifier on the server does 128 times 1 over what
No,
is
but
this?
you could do the 128 proofs in parallel on the verifier, no? On the recursive verifier?
So maybe
Oh, I
for
see.
example,
Okay.
so if you use some kind of forwarding scheme, or for example, in the recursion side, we only handle one gate verifier, and we combine multiple one gate verifier using forwarding scheme. One
Nice.
issue is if we use the same wire value for multiple gates as the input gates, we have to forward the same instance multiple times. So maybe it's a wasteful operation. But I think it's easy to parallelize the proof generation because its basic logic is gate by gate proof generation and verification.
Okay, so basically you're running like in this case 218 different versions of the circuit, and basically you fold each gate as its own like set of folding proofs, basically. Is that
So I
correct?
mean, so
No, you fold each circuit, not each gate, right?
I mean, theoretically we can for the proof for gate. So it just checks
Like which type of gate it is, and then it does like the right check
So-
here, basically.
so we consider so we first embed the gate type into the circuit or the recursion circuit.
Yeah.
And so for example,
Well, like the really simple way to do this is you just have all 4 of these gates inside of one folded circuit, and you just
Yeah.
check which type it is.
yeah
And you can do like a hypernova trick where you split them into
Yeah.
different stuff, right? Like you basically make a VM with these 4
yes
as your opcodes.
yeah yes,
basically.
yes.
So you have like a constant addition, constant multiplication, addition of 2 things, multiplication of 2 things.
So for example, the simple approach is we can put the get sorry right.
So do we do like 218 of them at a time, basically, in this one folded thing? Like we just check all 218 of these different things in one step.
Yeah.
Is that what you're saying, basically?
Yeah, so we can verify one circuit itself in one step, but we can also verify more smaller circuit in one step, and
Yeah.
for this instance, using folding scheme.
Right.
And one issue is we have to ensure that the given input value is corresponding to the input value of this each gate, and to that value is so we can output the get index value index as an instance, and the folding scheme. So for the circuit check if the given value is corresponding to this input value. But
Sorry, but adding a folding scheme makes it very difficult to verify on chain. The whole point of the recursion is to make it verifiable on chain.
yeah,
Yeah,
yes.
cycle fold is like 10 million constraints or something like this to verify a cycle fold proof.
Yeah. So
It's
if
like
there
really not that good.
the other approach is we use Plunkett recursion, and we make a small Plunkett circuit for a smaller size
Starkey circuit?
as Plunkett.
Isn't it like a base of Starkey things
Starkey.
and you verify with Plunky 2 or something? I might be getting
I
this wrong.
Yeah. So
Or Plonky 3.
yes.
Plunky 3 doesn't have this stuff built. They don't have like recursion. Plunky 3 is just like math. Is the way to think about Plunky 3. It's just like optimized math. There is no like larger setup. SP1 is the best way to use Plunky 3 right now, I think. But there's like a significant VM overhead for SP1. Anyway, so yeah, okay, so basically, so there's 218 different like full circuits that you need to systinctify. But I definitely believe that this is like extremely fast in a client because you're literally just doing like the computation.
But can you not just RLC the 218 together? Because this verification, like it seems like all 4 of them should still hold if you just RLC all the input values and just check it once.
Yeah, facts. Shouldn't that work?
Or
Maybe
So
the first
just-
3 yes, but I don't know the last one.
for first one.
Oh wait, no, you're doing different transcripts. Like each time you're doing a different index of the computation. Oh wait, no, but it's still the
So
same.
you're doing it
gate.
on every index. So did you understand my question?
Could you repeat it again?
So what I was saying was,
Nice. Oh whoa, that's
thank
so
you.
nice.
you might be able to RLC the all the gates together. So instead of having to do like 218 checks of each gate or whatever, you just do 218 like additions for the RLC, and then you do the check of all the gates.
Wait, but you need to prove that you RLC'd all the things correctly.
Yeah, correct. So you're anyways doing a bunch of constraints.
I don't think you can get around not doing each of the checks basically.
But then, why can't we just do this whole thing in Grot16? Fine, there's a 218 size overhead on the number of checks, but that's fine because you're on a server.
You're doing 218 Grot16 proofs.
No, you can do one Grot16 proof with 218 times the number of constraints. No.
Well, that's the same complexity wise.
Yeah, but it's cheaper on-chain verification wise.
Well, also the Z key would be so astronomically large that you're fucked.
The Z key's fine. It's all on a server. Who cares?
218 times like a repeated SHA circuit. That's actually getting to like a terabyte of fucking Z key.
Yeah, that might be pretty massive.
Yeah, I guess I'm unconvinced that the verifier can be like I completely believe that client-side proving cost is like insane, and this actually seems like a really good thing for off-chain proving stuff, and which maybe just makes it worth building anyway, because I think there are a bunch of good off-chain applications, but on-chain verification seems really hard, just from high-level intuition, because it seems like you basically need to constrain 218 times n, where n is the number of constraints you had originally, even if it's in the right field for your stuff. And I guess the other thing about changing to a different field from like the binary field, like 2 or 2 to the 32, is the number of constraints the client is doing is also a lot larger. I'm not sure at which point this like crosses where like, yeah, like it becomes, yeah, I don't know what the best trade-off is here, basically.
Wait, so yeah, what do you think?
So
this is also based on a 45-minute lecture on ZKBoo, so got 30% confidence in this opinion. This is really interesting though. Thank you for going.
Alright, thank you.
It's just like pretty. Like it's just a really nice scheme.
It's so simple.
Yeah.
Vol is really similar to this.
Yeah.
Vol is like, it uses a different tool other than this, like basically this is the main tool here is like you have a 3-party secret share.
Yeah.
Vol uses this like oblivious linear evaluation where you work with a verifier to come up with a bunch of OLEs for your circuit, and you do the exact same thing where like you verify all of the gates on these OLEs.
And you do 218 times.
No, you don't need to do 218 times, you just do it once.
Oh.
But the problem is there's this like high level of interactivity. Actually, there's high level of interactivity here as well. So Vol might just be better based on my also 45-minute deep dive.
I think because the recursive proof will be much smaller for Vol probably.
Or even prover time. Like in this case, the prover has to do 218 versions of this, right? Is that correct?
Sorry.
The prover is doing this 218 times as well, so it's a 218 size overhead.
So
which it's pretty cheap. It's just like math, or like there's no elliptic curve commitment.
Yeah. It's just like witness calculation 218 times.
Not even witness calculation. Just literally like, or like witness calculation also includes committing to the witness usually.
Yeah.
Is literally just going through the trace.
You also have to commit to the witness, no?
There's no committing happening.
I mean, no committing happening. Yeah, there is a committing happening.
The secret share is like you just split it up into 3 parts additively, and then
the prover needs to commit the whole transcript every time for each party.
Or
at the start you split your input into, correct me if I'm wrong, you split it into 3-part additive secret shares, and then you just compute on the secret shares.
No, but your fiat shamir is on the 3 commitments.
That's a hash.
Yeah, but you calculate the 3 commitments and you hash, and that's your fiat shamir challenge.
Okay, but there's no cryptographic commitments happening.
Correct, there's no cryptographic commitment. Give me like a hash.
It's just you do 1 hash compared to like committing everything to an elliptic curve value, which is like very
correct. It's 1 hash of everything. Yeah.
So I wonder if we can theoretically improve the recursion side, or instead of directly embedding the verifier circuit into Grot16 or some property.
Wait, say that again. Sorry. Wait.
So I wonder if we can improve the recursion side efficiency, or by seeing the more deep construction of the pairing based or GK snack schemes, or instead of directly use Grot16 or some existing schemes, or so
something that's more recursion friendly, basically.
Yeah. So for example, if we can, so can we, for example, if we can, so instead
what
of
happened?
directly,
Oh,
so instead of directly verifying each gate computation inside the ZK snack circuit,
Mhm.
if we can make some commitments and make some combination or
like an
so,
RLC basically.
yeah, as you said, and maybe it's the same as the existing forwarding schemes idea. But I'm so
I see what you're
I
saying.
think we have some potential to consider more optimized reschedule idea.
I think I see what you're saying. Like there seems to be like some tricks you can basically take from Nova
Yeah,
in the way that it like commits to witnesses
yeah,
to be able to handle the verification of these 200 instances better, basically. That makes sense to me. It's worth diving deep into. Yeah. But regardless, I think this like if you're excited about this, like I think just for off-chain proofs,
yeah,
this is still worth doing
yeah,
because this will make the hashing and a bunch of other things like really fast. But I guess wait, they already have.
Sorry, ZKBoo and binary field already got implemented for SHA and it was not very fast.
Oh yeah, what's the deal with that?
Yeah, why was Yingtong and Andrew's binary field implementation not fast?
I think she compared the benchmark with Stacky,
Right.
and
Yeah.
Stacky was faster than
Oh, but in the browser, ZKBoo still might be faster.
let me check.
Right. The memory usage of this is incredibly low. It's like
Yeah.
you just literally have to keep the state of 3 parties at each index.
Yeah, you effectively need no memory.
Yeah,
There's no persistent state.
I think so.
No, you need this. You need all the gates.
Oh yeah, you need the function definition. That's
that
nothing.
is small.
That's nothing. Yeah.
It's basically nothing. It's just a program.
Yeah. It's just like the size of your R1CS file, basically.
So she said, when we benched it on shared 256, the program was slower than Stacky, although they didn't implement plotting or also layer Bayfire. And
Oh yeah, that was one thing.
I'm sure
They didn't have what?
Like they were using fucking who's the guy from Nocturne? What's his name?
Sebastian.
Yeah, they were using his SHA-256 implementation, which like doesn't have like half the steps or something.
In Starkey.
Yeah.
Really?
So it's
In Plonky 2 or Starkey or something. I remember like also Jolt was angry about this or something.
That
Or, like,
Sebastian's implementation was incomplete.
yeah, there's like some issue, like you know the Celas, like the state of ZK
Yeah.
Celas network.
Oh, so Starkey was super fast for SHA-2 because they used Sebastian's buggy version.
I think it's just like it would just require a 2x, like whatever time they had is just time 2x basically or something like this.
Wow.
Anyway, like Srinath has an issue on their repo about this that was never resolved.
Really? On
It's
Starkey's
funny.
repo?
On Celas's the benchmarking repo.
That's unfortunate.
They were like, hey, like this is an unfair comparison against Nova because Starkey is broken.
Oh wow.
I see.
And they were like, yeah, we know. Lol. Basically, I had it open for a while actually. But recently closed. Yeah. What were you saying, Sora?
So
I found it. Where should I send this to? Should I have a channel for this stuff?
Yeah, we have a chat with Andrew during Yingtong for
Yeah.
ZKBoo.
Oh, can you add me to that actually?
Yeah. Oh, there's a bug. How does the bug get here?
yeah.
Oh, big disaster.
Where's the tissue papers? Sorry. Window?
Window?
Door?
Do you have a cup?
Oh no, I'm just saying like you can get it through the window. You should just kill it.
Oh.
Or put it down the toilet or something. Or you should hold it more closely. Yeah, nice. Just flush it. What a horrible death. Nice. ZKBoo was good. I think you should also look into Vol though.
Yeah.
Because I think it might be because in the Vol in the head, I think they compare it against MPC in the head and they say it's more performant.
Yeah.
And I think potentially might not require as many iterations of the
Yeah.
whole circuit. It might just require one
Yeah.
because you don't need to do this like there's not this like sort of 2/3 sampling basically. Is my very rough intuition.
Yeah.
Yeah. Cause here, yeah, this is so clean though. Wow, this is like such a nice little scheme.
So as a conclusion, how about trying the ZKBoo or for the first 2 weeks, and we can check how it is efficient, and if we find it's not so huge speed up, or its recursion circuits requires the tom circuits on GAUSS 16 or some GK snack schemes, we can consider some different approach. And
So I guess my concern here is that without some sort of like optimized RLC prover or something, I see no way that a recursive proof can be fast to settle on chain.
yeah,
And the other confusing
Or
thing
sorry,
is
cheap to settle
Yeah,
on
yeah.
chain.
why understanding better why Yingtong and Andrea's thing was so slow, because in the paper the benchmarks are nuts. Like the benchmarks are like we do this like massive SHA-256 digest in like milliseconds. But yeah. Wait, did they not just use the paper's implementation? What did Yingtong and Andrea like implement it from scratch? Also wait, can you add me to this chat?
Yeah, let me
yeah. So, but I think the motivation of this ZKBoo paper is when this paper was published, there's a few ZK schemes which can achieve the native field for Boolean computations, but many people want to compute the Shatz or such familiar computations on ZKB.
Yeah.
So if the paper says it's familiar with Boolean circuits, or many people, so it can take many attentions from the researchers. So I think this is why they focus on Boolean circuits.
I see.
But in this case, if you want to do SHA-2, Boolean circuits is the fastest.
Yeah, so if the stack is benchmark was broken, I'm not sure.
Oh wait, can I help you with the FutureWorks thing? Sorry. The FutureWorks. Scroll this way. Okay, allow. Click allow on this. What if we literally just like helped FutureWorks with their website? That would take 1 day of effort to like make it like approximately 6 times better. Okay, nice. Yeah, this is what you gotta do. I'm so confused. Sachin took a bus from the airport.
Yeah, you can take a bus from the airport in the
Kansai?
south, the one that Giannis came from.
Kansai?
Yeah.
Damn. Kansai is
concept much farther away.
Yeah, it's in the middle of the water.
Yeah.
Oh my god, it is so far away.
Um.
Damn. Yeah, it's literally an island. They just built an island.
Yes.
Sorry. One
Yeah.
thing.
And
What was I thinking?
dumb question, but what is the problem you are trying to solve, like by implementing an improving scheme?
Oh no. So this thing already implemented, but the point is you can do very fast client-side proofs because Circom's very slow in the browser client side, and it's because like one there's like a lot of memory that you have to take up, and so you can only do circuits that are so big, and two you have to do all these FFTs and MSMs because you're doing all these EC operations. And so the hope is that ZKBoo can fix both of those by making it very low memory and with no FFTs and no MSMs, so it can be super duper fast. But the problem is, if you want to recursively prove this, the proof size is ginormous. And so, okay, one question I have is, can we reduce 218?
Yeah.
Sorry, reduce what?
So one question I have is, currently, we're doing log base 2 of 3 because we're doing 2/3.
Yeah,
But what if we opened like, say,
No.
3 transcripts on 4 secret shares or something?
I see.
Then we would have to do,
Wait, 3 transcripts?
let's say you secret shared 4 times, you open 3 transcripts instead.
Okay, let me see.
Or something,
No,
sorry,
I
two transcripts instead.
Yeah.
Then you would have to do double the number of calculations,
Yeah.
but you would get, the person would have to fake 3 transcripts out of 4. So then my question is like,
So yeah, it gets higher. The
It gets
more you
higher.
secret share it, yeah.
sorry, what is the thing you calculated?
128 divided by log, like n of n plus 1, I think. Like in the paper it was 2 of 3. I'm just guessing this is how it scales, I don't actually know. But yeah. I think 2 of 3 is the best it gets. You can't do 1 of 2. Sad.
So
Sorry, it would be,
I think
This gets smaller, so this gets bigger.
here so repetition time will be smaller, right?
no, but why is it bigger?
Wait, what? What do you mean?
You have to you have to do it less than 218 times, or more than 218 times. It's harder to forge 3 out of 4 transcripts. Wait, what's wrong here?
I don't know. I also. Let's see. Oh.
No, inverse.
Oh.
You are doing inverse. Ooh.
I know this definition.
What's the deal here?
I think it's handling some RAM problem.
I just love this name, ZKBoo. ZKBoo.
Let me look at this calculation
So
again.
if we handle three of 4 MPC, then
Log 2 of 3 minus 1.
Wait, what is? Oh.
It's easy to see the function grows with n. One of their NPCs is anyway, why am I going so deep into this? Actually, I guess I care about ZKBoo slightly. For function things. Yeah, cycle fold with a circuit of, sorry, this is just reference for folding based verification. A circuit of 500k constraints, the decider circuit is 11.7 million. If you want to verify like a cycle folded instance. So, yeah, verifying folding stuff even with cycle fold is not great. Still like a pretty non-trivial server-side computation.
So okay then I think we don't consider using folding for recursion side and just use the cross 16 for entire circuit or
What was the last part?
also you simply use the cross 16 for the entire circuit or use some truncated recursion and then our question is how much actually how much how much constraints is required for the verified circuit of the ZKBoo and if we increase the number of open commitment or open views, we can reduce the number of repeating times because it's more difficult for adversary to estimate all random bits for each repeating time. But the verifier still need to compute the two views so the verifier still need to estimate two parties views if we increase the number of open views and my question is it possible to compress this two parties view computation into one party using some random linear combination like Frodic schemes? So for example, instead of we compute input A plus input B for each party, we can consider so input A plus randomness
times B
input B for so if we want to compute the view for first and second parties on the verifier side, the verifier samples randomness and instead of compute the input A plus input B for each party, it computes the so it receives the combined value of like input A plus randomness times first party's input A plus randomness times second party's input A, and it's the same for the input B, and it just adds these values. So and the verifier can check these constraints holds if the used commitment scheme is satisfies additive homomorphic properties.
Yeah, the thing is, like, Nova and all these schemes, they do additive and multiplicative, and this is why they're more complex. But the question is, you can have an only additive homomorphic kind of.
That's FHE. They just do additively homomorphic.
Nova.
Yeah. FHE. They're not doing FHE inside of the circuit. If you have both additive and multiplicative, you can do everything.
Right.
Which is like a lot of stuff.
Yeah. So I don't think we need free homomorphic commitment. We only need I think we should make this game only from additive world and
so yeah, at a very high level, I think there is promise. Yeah, that's all I can say. I have no idea if this is possible. Although it is true that the sort of tricks that Nova uses obviously were not available to these authors in 2017. So there might be some really clever blending of the stuff. Yeah. So why is this the case? between RLCs. The reason why it does additively stuff is because you just need to add one commitment with another one times R, and then put those together. So you only need addition.
Yeah, but doesn't Nova incur additional complexity from the constraints not all being the same? Or the constraints are all the same.
What do you mean constraints not being the same?
Oh wait, never mind. Oh yeah, this is basically just Nova. Oh, yeah, okay.
It's basically just
No, like it's like we make this like circuit for these like whatever, all your gates and this like process of all these multiplications and additions and everything.
Yeah.
And this is like the circuit that you're folding with Nova 218 times, and it's the exact same as like writing a circuit in Nova or Nova Scotia or whatever and folding it 218 times.
Yeah, exactly.
It's like the RLC process is the same because it's one gate at a time.
Yep. Yes, exactly. Yeah. We reinvented Nova. Let's go.
No, there's something different about the cross terms.
Cross terms.
Like something feels off.
So is this just R1CS? What they describe in the paper, Sora?
Sorry.
Can you represent their circuits as R1CS?
I think I
Yeah,
think
that's
so.
fine. Just plus and times.
Yeah, so we can think so we can assume the circuit is like given all witness value it's computes, it checks if there some ratios constraints are satisfied, and if and only if all constraints are holds it outputs the public input and outputs.
Wait, also for this secret share, are these like field elements, or are you committing? Are you like, is this like Pedersen commitments or something like this? How does the secret share actually work? Because if it's not just field elements, then actually verifying the meta sort gets horrible, right?
I think you can, so for example, you just sample two random values and define the sub share as original input value minus first share minus second share.
Right. And and to the first one you add both of them or something.
Yeah.
Oh, you just have R1 plus R2.
So sorry.
You have R1 plus R2, and then X minus R1, X minus R2. Those are your
Yeah,
three
yeah,
shares.
yeah.
And that just works.
Yeah, because it's it requires 3 shares to recover the input.
Yeah, makes sense. Nice. This is really clean. It's so pretty. But it's like, it's not even a narc, or it is a narc, but it's like a
Just no interactive zero knowledge protocol.
right, yeah. Nisink. With a pretty huge proof log, actually. Yeah, I guess the other thing I'd be very curious on is like how this compares to Volney head. Because in the Volney head paper they explicitly say it's like simpler, smaller, and faster than related approaches based on MPC in the head. So that seems like a worthy comparison as well. Because this is much more recent work. It's like this ZKBoo is like 2016, this is 2023. So I'd also be very interested in seeing how these compare. Let me see if I can find if they ever do a ZKBoo comparison. No, they don't.
Sorry, can someone explain this log base 2 of 3 thing to me? Like, how are they getting this?
So the article says the soundness error for each repetition
Yeah,
is
it's 2 there, yeah.
3, and so it means the Martian's prover can
succeed 2/3 of the time, yeah. Because they just don't guess the right, the one that they faked.
But I wonder why this is not 1/3, because if it can predict the bit E, or it can also automatically know the which two parties views are open.
But they only fully check the execution of one player.
Yes. Okay.
Does the second share main?
I see. So, okay, alright. So even if each
I'm not convinced though.
it need to determine two.
Oh, it says the gates only hold for the first player, but the gates may not hold for player 2 and player 3.
So it need to determine. It need to estimate which two parties views will be opened. And
so then for 4, it would be 2 out of 4.
Yeah. Party So if we increase this number of parties to 4, the verifier selects bit E, and the opened view will be E and E plus 1 and E plus 2.
Right.
And the probability will be 3/4.
Mm-hmm.
And this case, if it reviews the commitment,
No, yeah, it's worse because the chance, like, let's say they faked one of the rows, one of the users. The chance we catch the faked user with 3 parties is 2/3. Is 1/3. 1/3 of the time we'll catch that one.
Yeah.
But with 4 parties, 1/2. No, so it is better.
Yeah.
It's from 1/3 to 1/2. But then we double the amount of computation. So it's effectively 256 versus 218.
So sorry?
We do double the amount of computation though.
Yeah. So
So then to get soundness error 2 to the minus 128, we would do 2 to the 256. Sorry, we would do 256 iterations of this protocol. And
oh, sorry, this is unrelated, but I realized the answer to the addition XOR thing. But
is I didn't understand that.
basically, like when you have a binary field, then the elements are not usually, they're not represented like this binary extension field. They're represented as like
So this
polynomials.
binary field, you mean size 2 or size 2 to the 32?
Binary extension field, so like 2 to the k.
Yeah. Okay.
Field. These are not represented as like numbers. They're represented as like polynomials modulo some irreducible polynomial. So when you add 2 polynomials in a binary field, it's basically like either 0 is the coefficient or 1 is the coefficient. So
Oh, and the polynomial of the sum of like 2, 4, 8, 16, and so on.
What?
Like the polynomial x is 2.
So you mean if we consider extension of the field,
You guys can just read this fucking stack of result posts. I think this is different in a finite field
Yeah,
than a
yeah,
ring,
yeah.
basically.
So it means in the extension field it is calculated as the sum of the polynomial. So sum is calculated for each coefficient.
Yep.
Yeah, so it's the same as bitwise XOR.
Yep.
But if we just compute this one as a simple 32-bit computation, it need to calculate consider the carry of the each bit. So it does not equal to the bitwise XOR.
Exactly, yeah. And Binius operates on these binary fields specifically, whereas this protocol operates on the rings. So the addition operation is different, basically, I think, to make the different properties of the algebraic object work out. So that's why this is.
Sorry, what is GF2?
2, just like the finite field size 2.
So X is 2.
Huh?
It's a mod 2 finite field.
Oh, right. Mod. So the coefficients are mod 2.
Exactly, yeah.
So 101.
Because it's like a 1 plus 0x plus 1x squared.
So I want to represent the sum of two 32-bit numbers.
Yeah.
How do I convert the 32-bit number to this 1 plus x squared form?
So it's just like if there's a bit on the ith index, then you add x to the I.
Then you add x to the I. Yes. Okay. Right. So it's just a binary decomposition.
What's a binary decomposition?
Oh, like whatever. Like if I have the number 7, it's like 1 plus 2 plus 4. It's like 1 plus 2 plus 2 squared.
Binary, and then you make those
the coefficients of the polynomial.
Yeah.
And then when you add the two polynomials, mod 2.
Well, you add the two polynomials, and then their coefficients are all mod 2. Yeah.
Why are their coefficients all mod 2? Like
this is just how you describe finite fields for non-prime sizes.
Okay, but 2x squared is not 0 mod 2 to the 32.
No. It's 0 in the finite field. Like the finite field is defined. We're not thinking about numbers anymore. Like this corresponds to 101, but like they are not the same. Like we're basically like indexing all these elements essentially. And these will all form their own finite fields modulo some irreducible polynomial. Okay, nice. This like finally just clicked for me. Cool.
Sorry, this has not clicked for me.
It's fine. This
Very
is like
dumb.
vaguely deep abstract algebra. And it's also like only relevant in AES and fucking Binius. Amazing. Okay, so also this also relates to Olvatana rebranding as irreducible.
What?
Like the company that made Binius recently rebranded from Olvatana to irreducible.
Ah.
And it's because you make binary fields by taking polynomials modulo some irreducible polynomial. Nice. Oh my god, that feels so good. This finally makes sense. This is such a guy. You guys trying to get food?
Here.
Yeah, I'm pretty hungry. That lunch was not filling.
The udon place across the street is really good.
Extremely down for some udon. We might not be able to
Yeah, the problem is it has to be empty at dinner time. Chance being 0.
Yeah.
Or have you ever eat octopus?
I don't like
tried
octopus.
before.
Right.
I thought it was okay.
I don't like octopus.
Do you like octopus?
Yes. So, one famous local food of in Osaka is it's a takoyaki. It's a kind of food using raw octopus.
Right.
And
It's like dough, right?
yeah, dough, yeah, flour dough, and inside that there's octopus.
Make some down, actually. Yeah.
I don't like it that much.
You don't like it that much?
I don't like octopus very much.
Something else then. Nice. Learn ZKBoo. Let's go. I want to have a tracker somewhere where people can be like, I learned this thing.
That would be
Should
cool.
we make a chat? Like just a channel that's just like.
Why don't we do a survey at the end where we put in all the topics and people just mark if they know it or not?
That's so boring. I'm not gonna fill out a form. I
What?
want to be able to share like, yes, I learned this thing. Let's go.
We can make it like a live streams channel or something, or like a lessons channel, like a workshop.
Also, can
channel.
we make a Twitch channel for the residency?
Yeah, currently it's just my current Twitch. That's true. It's kind of tricky to share because then I just dox myself on Twitch. People go watch. I'm like degenerate gaming.
Yeah, we'll just make a different Twitch for the residents.
Yeah, I'm down.
It's currently 4 a.m.
There's a lot of izakaya here.
It is Japan. Oh, sorry. I also have another proposal for fast clients and ZK proofs, ZK email proofs.
Yes.
Which maybe I can share after dinner.
Yeah.
Let's eat first. My body's like crashing. I simplified the proposal from what I shared with you. I think you can do everything in 2 proofs.
Oh.
And I think the DevX is also way better of like writing this all out. Also, can you guys do introductions in the channel?
Okay, yes.
It does not need to be. You can take a total of 30 seconds. Just write something about yourself and link to your project, if possible, in the Telegram. You don't need to follow the format. That was just for some structure.
I'd rather just walk and then Sora just points out like, or Sora and Nico just point out like, oh, that looks good.
I feel like I'd rather have a place in mind because for lunch we tried this and I guess, I don't know.
We can have Sora and Nico for lunch. That was the difference.
Yeah, so I think
Yeah. Do you have a recommendation for food nearby?
When we're going to this place, I can see many local food prices in front of station. So
Mm.
Should we just go there? We'll do one of them.
maybe.
Takeaway might also be the move potentially if we get to a place with takeaway, because then we don't need to like get seating. We can just bring it back here.
True.
I'm down for some noodles.
Noodle is also fine.
I like soba. I like ramen. I like udon. Most noodles work well.
places don't have takeaway actually.
So I think one of the famous order food is like these things. So it's
Which thing?
I think it works pancake, but it does not sweet one. So it has it's a
Okonomiyaki?
yes, exactly.
Oh. Do
So
you have
it has-
these? We had them in Vietnam.
Yes, we eat it in Vietnam. So it has flour with some meats and some vegetables, and we fry it on the iron plate, like yeah, right this way.
Nice.
And
That seems quite good.
yeah, there are many junky foods.
Nice.
Interesting. The fish place right downstairs is apparently very good.
Which restaurant?
The Crab House?
Yeah,
Ah,
I think so. Crab House something. Is this one? Is this Crab House? I don't know. What is this?
Let me check it. Yeah, so it's a crab house and kind of fish.
Fugu puffer fish? Is that it?
Let me check the English name.
Oh, dude, the udon place is only open until 3 p.m.
Oh wow.
It's like a lunch spot.
Yeah, it's a puffer fish.
Yeah.
Oh, nice. You exactly nailed it.
Yeah, so
Restaurant said.
Yeah. I will let Anna try it. I'll pass. I'll pass on.
so crab tastes very good.
Crab.
Crab, yeah.
Okay.
But one problem is, it takes many times.
A lot
Because
of
you
time.
have to you have to pick the meat of crabs from the
Oh, that's a pain.
yeah.
And we have to do that.
Yeah. But,
Oh.
maybe I'm not sure, but yeah. So usually we pick these meats by ourselves, but I'm not sure it's the same in the restaurant.
I see.
And if you want to eat noodles, there are many kinds of noodles.
Infinite noodles.
There's a place called Hankyu Soba.
I see.
What's that?
Is there any page to like post
Okay.
recommendations?
Oh, yeah, there's a food
But I
channel.
think it's
Oh.
very
Please post, yes.
I see. So, but actually, in the west area of Japan, I recommend udon rather than soba.
Ah.
Yeah. So,
Okay.
so udon is I think
Better
you should
here.
eat soba in east area like
I see,
Tokyo,
okay.
and udon in the west area.
Cool. The problem is I don't think there's any udon near us. We can just go to the southern the station, right? This is
Yeah.
whatever, plus 5 minute. And then there's like a million things in the station.
But the thing is, they're all like, all the good ones are full.
No, it's fine. We wait like 5 minutes, no big deal. There's a ton of udon restaurants down near the station. I'm down to go. And they're all ranked very well. Like 4.5, 4.3. And there's no udon where we are right here.
Yeah.
Just this one right here.
You mean DCL, right?
Like, wait, I
Or
don't
it's
know.
a
Zoom out.
udon restaurant.
Zoom out. Oh, that's udon.
Yeah, it's a udon restaurant.
When you search udon in Japanese, you get so many more results.
Really?
Yeah.
So
What?
I think this
When I
one
searched
is
in English, I got
closed,
nothing.
but many restaurant is closed.
Yeah.
So So there were two enterprises, and both of them has 4.2 points, and it takes about 12 minutes to walk.
Sweet. Let's do it. Should we just walk in that direction? If we find a place that looks good, then we go there.